Hello everyone and welcome back. Welcome back to the channel. Today we are diving deep into the world of electric drives, focusing on three critical aspects that every engineer, student or enthusiastic should understand. Equivalent drive parameters, friction and load torque. These elements are the backbone of motor performance, system efficiency and predictive behavior in various operating conditions. Whether you are working on industrial robotics, electric vehicles or wind turbines, understanding these concepts is essential. So grab a notebook because this is going to be a technical and insightful session. Let us start with the motor equivalent circuit parameters. Every motor can be represented by an equivalent circuit, and understanding these parameters is key to analyzing and optimizing motor performance. The three main parameters we will discuss are stator resistance, rotor resistance and leakage reactance. First up, stator resistance. This is the resistance in the stator windings and it's responsible for power loss in the form of heat. A higher RS means increased losses and reduced motor efficiency. So when designing or selecting a motor, keeping stator resistance as low as possible is crucial for optimal performance. Next we have a rotor resistance. It is denoted by R suffix small r. This parameter plays a significant role in determining the motor's starting torque and slip characteristics. By adjusting this resistance, we can optimize the motor for specific applications such as high torque starts or smooth operation under load. Finally, leakage reactance, that is XL. This arises from the magnetic flux that does not link both the stator and rotor windings. It limits the motor's power factor and affects its ability to deliver reactive power. Managing XL is essential for improving the motor's overall efficiency and power delivery. Now let us shift our focus to friction. Friction is an inevitable part of any mechanical system, and understanding its type and effects is crucial for designing efficient drive systems. There are three main types of friction we will discuss. First, static friction, kinetic friction, and viscous friction. Now, static friction is the force that prevents a stationary object from moving. It's the initial resistance you need to overcome to get things moving. The coefficient of static friction is typically higher than kinetic friction, which means it takes more force to start motion than to maintain it. Once the object is in motion, kinetic friction takes over. This is the force that opposes the movement of a moving object. It's generally constant and proportional to the normal force. Kinetic friction converts mechanical energy into heat, which is why managing it is crucial for energy efficiency. Lastly, we have viscous friction, which occurs in fluids like oil or air. It's proportional to the velocity of the object and is common in lubricated systems. Viscous friction can be both a friend and a foe. It helps in damping vibrations but can also lead to energy losses if not managed properly. Now that Now that we understand the types of frictions, let us talk about modeling friction in drive systems. Friction is often modeled using equations that relate the frictional force to the normal force and the coefficient of friction. These equations help us predict and compensate for friction in drive systems. In practice, factors like surface roughness, temperature, and lubrication can significantly affect the coefficient of friction. For example, proper lubrication can reduce friction and wear, improving system efficiency and lifespan. On the other hand, high temperatures can increase friction, leading to more energy losses. To counteract the effects of friction, engineers use various compensation techniques such as feed-forward control and adaptive control. These methods aim to improve the accuracy and responsiveness of the system by compensating for friction in real time. Proper compensation can significantly enhance performance and precision, especially in high precision applications like robotics or CNC machines. Let's talk about now the load torque. Load torque is the load torque is the torque required to drive a load connected to a motor. It represents the resistance the motor must overcome to maintain motion. Load torque is a combination of constant and variable forces, and understanding its source is crucial for motor selection and system design. Mechanical loads such as gears, belts, and pulleys are common sources of load torque. These components introduce friction and inertia, and the motor must overcome. Proper selection and maintenance of these components can reduce their impact on the system. The environmental factors such as air, resistance, and fluid viscosity can also contribute to load torque. These factors are particularly significant in high-speed applications or harsh environments. For example, in electric vehicles, air resistance increases with speed, requiring the motor to work harder to maintain velocity. Now let us discuss the impact of load torque on motor performance. Load torque directly affects three key aspects of motor operations. First is speed variation, then current drawn, and thermal stress. Speed variation occurs when increased load torque causes the motor speed to decrease. This is because the motor has to work harder to overcome the resistance. Managing speed fluctuations is crucial for maintaining energy efficiency and system responsiveness. Now, what about the current drawn? The current drawn is another critical factor. Higher load torque requires the motor to draw more current, which can lead to increased heat and reduced efficiency. Managing heat becomes essential, especially in high load applications, to prevent motor failure. Finally, the thermal stress is a major concern. Excessive load torque can cause the motor to overheat, leading to thermal stress and potential damage. Proper cooling and load management are essential to prevent motor failure and ensure longevity. Now, to effectively manage load torque, we need accurate methods for measuring it. There are three main techniques we will discuss: dynamometers, torque sensors, and current monitoring. Now, what are dynamometers? They are commonly used to measure load torque by applying a controlled load to the motor and measuring the resulting torque. These devices provide accurate and repeatable measurements, but they require precise calibration. The torque sensors can be installed directly on the motor shaft to measure load torque in real time. These sensors provide continuous monitoring and feedback, making them ideal for applications where real-time torque control is critical. Finally, current monitoring is a less accurate but more accessible method. By monitoring the motor's current drawn, we can estimate the load torque. This method is useful for rough estimates, but it requires calibration with known torque values. To wrap up the things, let's look at some real-world case studies where understanding equivalent drive parameters, friction, and load torque is crucial. First, industrial robotics. In robotics, precise control of friction and load torque is essential for accurate movements and smooth operation. Effective friction compensation improves positioning and stability, which is critical for tasks like assembly or welding. Next is electric vehicles. EVs require efficient drive systems with minimal friction to maximize range and performance. Understanding and managing load torque is critical for optimizing energy consumption. Low friction designs improve energy efficiency and extend the vehicle's range. And finally, wind turbines. Wind turbines experience varying load torque due to changing wind conditions. Accurate measurement and control of load torque are necessary to optimize energy capture and prevent damage to the turbine. Precise torque monitoring protects against overloads and failures. And that's a wrap up. We have covered a lot of ground today, from motor equivalent circuit parameters to to friction load torque, and real-world applications. Understanding these concepts is essential for optimizing motor performance and ensuring system efficiency. If you found this video helpful, don't forget to like, share, and subscribe for more technical deep dives. And as always, feel free to drop your questions or comments below. Thanks for watching.